Hi everybody, welcome to our review for section 5.2. We'll start as usual with, definitions and formulas that we need for this section. And here they are. Alright, so the difference between this section right here and section 5.1 is that in section 5.1, usually you make an investment or a deposit, and then you kind of just let it sit there for however many years, right? And just let it collect all this interest and then see how much you have at the end of that time period. Whereas in this section right here, we're making payments, so regular payments, which is the definition of an annuity. Here you see a sequence of payments made at regular time intervals, and those time intervals are dependent on what the question tells you, whether it's annually, semi-annually, quarterly, weekly, monthly, daily, and so on, right? But you're making the same payment every single time at the end of every period. And the first part here is asking us what is the future value of that annuity, right? So that you got to figure out what the difference is between when a question is asking you what is the future value versus what is the present value. And as you can see, the formulas are definitely different. So you just gotta be careful. Some questions will literally ask you to find the future value of an annuity or find the present value of an annuity, but most questions don't really do that, right? You just kind of have to get used to doing enough of these problems to figure out the difference. And hopefully, after we've done some examples in this section, you can tell the difference between whether a question is asking for a future value versus the present value. So let's look at some examples right now and see if we can figure out which formula to use when. All right, so this first question here. All right, so we have two people, Karen and Matt. They're both making payments or really depositing money into an account. So same conditions for the accounts that they're depositing their money into. We have a 3% rate right there, compounded monthly. So this information right here is the same for both of them. So I'm going to go ahead and write that down. So I'm going to say R is equal to 0.03, so that's the 3% there. Compounded monthly implies that there are 12 periods, so M equals 12. Okay, so we have that. Now let's look at information, more information. So Karen is depositing $170 at the end of every month since she was 24. And then Matt was depositing $240, and that was when he was 33. And ultimately, we want to answer the question, who will end up with the larger retirement account at the age of 65? All right, so here the assumption is, because it says who will, is that we're finding a future amount here, right? Maybe we're just assuming that they're not 65 yet, but when they're 65, who will end up with more money than the other? Is it Karen? Is it Matt? So the easiest way to determine this is to actually figure out how much money Karen will have and how much money Matt will have, and then compare the two values. So because we know that we're calculating a future amount, we know that we're supposed to find this future value of an annuity, which is given by S, right? So that formula we had in the previous slide. So S is equal to R times 1 plus R over M to the power of MT minus 1 divided by R over M, right? And of course, the textbook would say I is equal to R over M, and N is equal to MT, and it will just use I and N, but I prefer to just use the longer version of this so we can see where everything goes. All right, let's do Karen first. So Karen, all right, she's depositing $170 at the end of each month, meaning her payments, so those would be the value of R right there, is 170, right? So in our definition, those are the regular payments there, 170 for Karen. We know R is equal to 0.03. We know M is equal to 12. What else do we need? We need a T. That's all that's missing. All right, so how many years is she making these deposits of $170 for? Well, we know she started when she was 24. And we know that, well, at least for the sake of this problem, she's going to stop making these payments at the age of 65. So we're just trying to figure out what is the difference between 65 and 24, right? So you subtract the two, you end up with a 41-year period. So T is equal to 41 years. Now we have everything that we need. We can say S is equal to 170 times 1 plus 0.03 divided by 12 to the power of 12 times 41 minus 1, and then divide it all by 0.03 divided by 12. So once you do that, we calculate this, and it comes to approximately, so we're going to round to the nearest cent. That ends up being 164,286.79. Right, so that's if we're being asked to round to the nearest cent. Of course, you could round to the nearest dollar if the question asks you to do that, and you'd say $164,287. All right, so that's how much money Karen has by the time she's 65. Let's do math. So now for math, all right, so same conditions. R is still equal to 0.03. M is still equal to 12. All right, but now let's figure out what R is for Matt. He's making payment of $240. That's his value for R. Let's figure out how long he's making these payments for. So that's T. So he starts when he's 33 years old. He stops when he's 65, which means that's a 32-year period. And now we have everything. So we say S is equal to 240 times, we get 1 plus 0.03 divided by 12. So this part is the same, except now we have it to the power of 12 times 32. Subtract 1 and divide the whole thing by 0.03 divided by 12. And then when we calculate this, that comes out to around $154,000, 422.67 if we're rounding to the nearest cent. And if we're rounding to the nearest dollar, it's $154,423. Then you look and see, okay, so this is by the time they're both 65, who has more money? Well, obviously, Karen has more money. So Karen ends up with the larger retirement account. And hopefully that kind of makes sense. Even though Matt is putting away more money per month, he waited until much later on. He waited 9 years after Karen was already making deposits to start making his deposits. So even though they're much bigger, it doesn't make a huge difference in the end because Karen ends up with the most money here. All right, so Karen wins. So that's an example of using this future value formula. Let's get an example using a present value formula. So our next example is this one over here. Okay, so we have Lupe made a down payment of $6,000 towards the purchase of a new car. So whenever you see down payment, just know that whatever you calculate, you have to add that amount to it. Just keep that in mind. All right, so to pay the balance of the purchase price, she has secured a loan from her bank at the rate of 6% per year compounded monthly. So already so far, I know that down payment equals 6,000. All right, what else do I know? I know R is equal to 0.06 and then compounded monthly. So I know that M equals 12. Great. All right, so under the terms of her finance agreement, she's required to make payments. So you see payments, that's your value of R of $440 per month for 36 months. Well, okay, 36 months is really just that will be the value of N in the version of the formula for this. But the way I want to write this is I want to say T is equal to 36 months. But then because I like to keep T in years, because that's just standard, we'll say that's 3 years, right? So the value of t is equal to 3 in this problem. So 36 months, 3 years, t equals 3. Okay, let's figure out what we need to find here. So we're trying to figure out the cash price of the car, right? So this is I guess our hint for knowing that we're finding the actual, right, present value of the annuity. We're finding the present value of the car price right now, present value. So what you want to set it up as is you want to say cash price would be equal to the down payment plus present value. So present value P of the annuity. So once we add up those two numbers, we'll get the answer that we want, right? So that's equal to down payment, we know is $6,000, plus now we need to set up the present value P of the equation. So I'll come over here and then remind us again what the equation for P is. So remember, P is equal to R times 1 minus 1 plus R over M to the power of minus mt, and then everything gets divided by R over M. All right, so we want to use that formula. So over here, R 440 times 1 minus 1 plus R 0.06 divided by 12 to the power of minus 12 times t, which is 3 years. So we'll get back to the 36 there, well, minus 36 in this case, divided by R over M, so that's 0.06 divided by 12. Okay, so when we do 6,000 plus this whole thing over here, what I end up with in dollars is approximately equal to $20,463.25. Right, so what I got for this part right here, 400 times this stuff right here in brackets, was $14,463.25, and then I added to that the 6,000 down payment. So don't forget about the down payment. So if you're not given anything about a down payment, of course you will just figure out that value of P, which is this part over here. But we have to remember that there was a down payment, so the total price for this car is gonna be the sum of those two numbers, right? So this is the total price of the car. So just be careful with the wording of the problem, right? But that's the difference between when we use the future value formula versus the present value formula.